Hello, I'm Susan Nash, AAPG, and you are watching our Science and Technology Showcase. I'm happy to introduce our guest today, Dave Tonner. He's he's going to talk about hybrid mud logging, and he's with Diversified Well Logging. Welcome, David.
Good afternoon, Susan. Thank you.
So, how did you get interested in mud logging?
Well, I studied geology at Nottingham University, and I had a really inspirational high school teacher, Keith Hamilton, who had the most wonderful rock and mineral collection, and he was the person that got me interested in geology, and that led to my first job working in mud logging, which happened to be in Kenya for Amoco on the border with Ethiopia in the Chalbi Desert. They were drilling a 27,000-foot exploration well into
Wow.
into some Devonian orthoquartzites, which was it was a very exciting initiation to my rig career. So
That sounds like a bit chewer.
it was.
Anyway, well, tell us about hybrid mud logging.
Yeah, look, so mud logging hasn't really changed much in terms of rock collection and analysis, really since spindle tops. Buckets and trowels and people looking down microscopes and making visual estimations of what is in the rock. And there's some really good mud loggers, by the way, and it's a very noble profession. However, it is a little subjective and qualitative, and it varies from person to person, day shift to night shift, well to well. And so it makes it difficult to be used as a correlation tool and to be able to bring it into a workflow where petrophysicists can upscale it to seismic and really make sense of the data. And so what we've done is we've started to automate some of the processes, and step one is quite simply deploying a portable benchtop XRF, as you can see over here.
Oh,
Uh,
nice.
yeah, and so that gives us up to 42 elements and both major oxides and trace elements. And we can generate things like a gamma ray, which you can see over here on this curve, where the red curve is simply by adding uranium, potassium, and thorium, the gamma ray of the rock that we're actually measuring. And we can compare that to the MWD gamma ray in green. And so we know that the rocks are actually coming from the depth that we think that they're coming from. So that's the first phase.
Nice.
And then the next step is that, from that we can generate a model mineralogy. We can make estimations of mechanical strength. We can get indication of clay typing. So is it, do we have glauconites? Do we have illites? Do we have mixed layer clay smectites? We can get indication of reservoir quality using things like silica over aluminum. And we can measure matrix grain density and estimate bulk density. And so it's a data set that really grows a lot of legs and provides a window into the subsurface that, we really haven't been able to see on a regular basis before. And, some of the things that we're then doing is applying data science, like in this particular example, a random forest data science approach allows us to define formation tops based on the elemental composition. So a step further in taking the subjectivity of what somebody thinks is in the rock and replacing it with something much more quantitative and much more scientific. And so,
So you
that, yes,
so you can build in uncertainty into your model with that.
exactly, yes. And so with that, we can start to do things like geosteering, and we can do it both manually in step one and actually move to full automation in step two. We start to then also be able to impact drilling efficiency. So we can look at the unconfined compressive strength estimated of the rock, i.e. what force is required to break the rock, as you can see here in this blue curve, versus the actual mechanical specific energy being delivered by the drill bit. So it really is a marriage of geology and drilling, which is often sometimes there's some friction in those relationships, but the ability to provide the data in a way that the drilling engineer can consume and use makes it a lot more practical. And the same on the completion side. So we following the same workflows and processes where we go from elements to minerals to hardness to unconfined compressive strength. We can also deliver that information in a way that a completions engineer can utilize and optimize completion design for maximum performance.
Oh, that's very impressive.
Yeah, and it really, and then the next step is to actually then go into production forecasting. And so, you know, we can take the whole reservoir, we can input your major information required in terms of pressures, permeability, temperatures, offset well data, actual production information. And we can start to then see what moves the needle in terms of improved productivity, whether it's stage spacing, clusters, number of perforations, and then also put in the actual rock data to see how that is impacting both the daily flow and cumulative flow and EUR to be able to make the best decision. So it's very much about breaking down silos between disciplines and making a very fast and nimble process so that you know, reservoir managers, engineers, asset managers can make better economic decisions.
Oh, that's great. So it looks like you're using AI for not only classification and identification, but also for prediction.
Absolutely, yes. And that obviously plays a part as well into drilling optimization, where we can start to do much more analysis of which particular benches, for example, might have higher rates of penetration or less drilling dysfunction or less downhole tool failure, and link those processes together.
Oh, that's great.
And then, you know, one of the things that we've been focusing on, and we're fortunate to have a rich history in deepwater, but we've actually started to use an integrated approach to chemostratigraphy, or the use of XRF elements, and biostratigraphy, micropaleontology,
Oh, wow.
to build up a very comprehensive picture of compaction, rates of sedimentation, seal qualities, and how that relates to wellbore construction. For example, are we seeing more hole instability? Are we seeing increases in pressure? And the hole stability issues, poor pressure, geomechanical related problems, you know, are at least $1 billion MPT problem to deepwater Gulf of Mexico annually, according to information, publicly available information. So it's a significant problem. And, you know, we, down on this bottom chart here is actually an example of what we're doing in offshore in Mexico, where we're actually using a combination of biostratigraphy and chemostratigraphy to pick the tertiary Cretaceous boundary, with the objective of seeding the casing at that point, because there's a huge pressure regression from 16 pounds per gallon down to 6. And so picking that point for casing is pivotal to the economics of the project.
Oh my goodness, yes. Well, I'm also thinking that with this integrated approach, it could definitely help with reservoir connectivity in the case of turbidites, things like that.
Absolutely, yeah. You know, you combining the mud gas data, you know, C1 to C5, mass spectrometry up to C10, aromatics, inerts, nitrogen, CO2, hydrogen, helium, you can start to understand compartmentalization, connectivity, and look at that both within the well as well as across the field. And, that's also a major issue in deep water turbidites.
Absolutely. Wow. This is great.
Yeah. And then, the other aspect that we've been working on is also using digital microscopy and image recognition software to, again, give quantitative estimations of color, morphology, and that includes obviously the size, the shape, and we can start to look at things like angularity, sphericity, elongatedness. So the things that you would normally tie into wellbore stability, i.e. in an abnormally pressured shale where you would see concave, convex, elongate cavings, we can start to apply AI and image software recognition to, again, take away the subjectivity, make it faster, more reliable, and then immediately build that into a model to understand what are the implications in terms of, do I need to increase mud weight, decrease mud weight, apply more back pressure in order to maintain wellbore stability. So, there's a lot of people doing AI. It seems it's sort of like, the buzzword of the day, and it's all very fashionable. But, my experience has been that it's really about the practical application, and having the right sort of subject matter experts and data scientists together in a small team like ours allows us to act very quickly and nimbly, and we know exactly what we're trying to get to. And so, we're not spending a lot of time on, what if scenarios. We understand the use cases, we understand the problems, and that allows us to get to, to the use cases and value to our customers a lot faster.
Oh, absolutely.
Yeah, and but we're not stopping there. Like, what's actually really exciting is we truly believe that the future's automated, and it's going to be about the automation of services and analysis of cuttings and other things, and delivering a RAS, or robotics as a service, which is what we
I love that.
are looking to do with our RoboLogger, right? So we actually have a machine that can collect samples automatically every 2 minutes, so very fast. So even at high rates of penetration, you can get very good depth resolution. And the next phase, which we're actually working with Shell Game Changer on, is incorporating a LIBS laser. And you can see it's the same sort of lasers that are on the Mars rover project with NASA. And we're getting, again, up to 42 elements and minerals. And so we're able to create a very high resolution window into the subsurface, as you can see from this chart here, where we're actually comparing the RoboLogger collected samples and analyzed with XRF to the green curves, which are the core, which were analyzed by the Van Gotten Laboratory lithoscanner. And so it's a really interesting breakthrough. The next phase is to fully automate the elements and minerals, which is the inclusion of the LIBS laser. And we're looking at have field deployments of that device in late Q2 of this year. So,
wow. Well, if you had the pivot away from the oil industry, I can see how the RoboLogger and robotics as a service, you could use this in construction for integrity when it's based on the materials.
Yeah, I agree. I mean, I think there's also applications in mining, in some of the rare earth elements and metals, for example, for use in batteries for electric cars. And in fact, if we replaced our current fleet of 100 mud logging units with RoboLogger, just the reduction in movement of people would save about 10,000 tons of CO2 equivalent annually. So it's also good for the environment.
That's wonderful. That's incredible.
And yes, so that's, I mean, those are the things that we're, we've been working on, and Really appreciate the opportunity that you've given to us to talk about it with the AEPG.
Oh, well, we really appreciate it. It's impressive to see what you're doing, and I think important for people to have the opportunity to be inspired and have an idea of how far you've taken this. So thank you.
Thank you, Susan. Very much
So,
appreciated.
no problem. Well, thank you again. And for everyone who's watching, we've been having a wonderful conversation with Dave Tonner, and he's with Diversified Well Logging. And we're looking forward to reading the written interview as well. So thank you.
Thank you. Have a nice afternoon.
Thank you. Well, I hope that the airplane going ahead, I have my door open because it's such a nice day, but of course there's no plane traffic and now just when I'm recording.
Okay, so is that good?
You did great. Yeah. So it'll take me a while to process it, but you did a great job, and I'll put it, and I've got your written interview, so I'll send that in and the images. So thank you.
Thank you, Susan. I appreciate it very much.
Great. Well,
Okay.
we'll keep in touch.
Okay. Have a nice afternoon. Bye.
Thanks. Bye.
Bye.